NASA engineers thought they had lost Voyager 1 forever in November 2023. The spacecraft, humanity's most distant ambassador, suddenly started transmitting gibberish. Not silence, not a clean failure, gibberish, ones and zeros, arranged in patterns that made no sense, as if the probe's ancient brain had finally succumbed to decades of cosmic radiation and was now babbling incomprehensibly into the void. For 5 months, the team watched helplessly as their 46-year-old spacecraft, located 15 billion miles from Earth, sent back data that resembled the digital equivalent of a stroke victim trying to speak. Engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, some of whom weren't even born when Voyager launched, stared at their screens in disbelief. This wasn't supposed to happen. Not now, not after everything Voyager had survived. The spacecraft had endured Jupiter's lethal radiation belts, crossed the termination shock where the solar wind slams into interstellar space, and operated continuously in an environment where temperatures hover just 3 degrees above absolute zero. And then, against every reasonable expectation, they fixed it. They diagnosed a corrupted memory chip, uploaded a patch across 22.5 hours of signal delay, and brought Voyager 1 back from what should have been permanent brain death. But here's what that near-death experience really revealed. Voyager 1 is dying, slowly but inevitably, and we're watching it happen in real time. In this video, we'll explain how Voyager reached the edge of our solar system, why keeping it alive is one of humanity's greatest engineering achievements, what that November 2023 glitch taught us about deep space communication, and what will happen when it finally, inevitably falls silent forever. Let's get started. When Voyager 1 launched on September 5, 1977, from Cape Canaveral's Launch Complex 41, nobody expected it to become the longest-running space mission in history. The primary objectives were straightforward and deliberately modest. Fly past Jupiter and Saturn, photograph their moons, measure their magnetic fields, analyze their atmospheres, and then drift into the darkness as a relic of 1970s engineering. The mission was supposed to last 4 years, maybe 5 if the hardware held up longer than expected. It's now been 47 years. Voyager 1 wasn't even the most advanced spacecraft of its era. It was built during an age when computers filled entire rooms, when data storage meant magnetic tape, and when the idea of a smartphone would have sounded like science fiction. Its main computer, the Computer Command System, has 69 kilobytes of memory. Your smartphone has millions of times more computing power. Its digital tape recorder can store about 536 megabits of data, less than a single high-resolution photo on a modern camera. It communicates using an 8-track tape player to store and play back data, technology that was already obsolete when the spacecraft launched. The entire spacecraft weighs just 1,592 pounds, about the same as a compact car, and most of that weight is structural support and fuel. And yet, this ancient machine, built with slide rules and hand-drawn blueprints, has traveled farther than any human-made object in history, crossed into interstellar space, and continues transmitting data from a region no spacecraft was designed to survive. The reason Voyager has outlived every prediction comes down to 3 factors. First, brilliant initial engineering by a team that understood redundancy and robustness better than anyone before them. Second, a power source that degrades slowly and predictably, buying time measured in decades rather than years. Third, a mission team willing to perform increasingly desperate acts of long-distance surgery on hardware they can barely control, making decisions that would have seemed impossible when the spacecraft launched. But none of those factors can stop the inevitable. Voyager 1 is running out of power, and when the lights finally go out, humanity will lose its only functioning probe in interstellar space. The spacecraft's fate is written in the immutable laws of physics. Plutonium decays, electronics fail, distance makes every repair exponentially harder. We know exactly how this story ends. What makes it profound is that we're watching it unfold in slow motion, month by month, year by year, powerless to change the outcome. Voyager's power comes from 3 radioisotope thermoelectric generators, or RTGs, devices that convert heat from decaying plutonium-238 into electricity. These aren't nuclear reactors in any conventional sense. They contain no moving parts, no fission reactions, no control rods. The plutonium simply decays naturally, releasing heat as alpha particles, and that heat gets converted into electrical current through thermocouples, devices made of dissimilar metals that generate voltage when one side is hot and the other is cold. When the spacecraft launched, these three generators produced 470 watts of power combined, enough to run all the instruments, the radio transmitter, the heaters, the attitude control system, and the computers simultaneously with power to spare. Today they produce about 249 watts, barely enough to keep the critical systems functioning. The plutonium decays at a predictable rate, losing about 4 watts of power every year, and there's absolutely nothing anyone can do to stop it. You can't recharge plutonium, you can't replace it remotely, you can't slow down radioactive decay. The power budget is fixed, declining, and non-negotiable. Every watt matters because Voyager operates in an environment where temperatures drop to minus 270 degrees Fahrenheit, just 3 degrees above absolute zero, the coldest possible temperature in the universe. Without heaters, the hydrazine fuel lines freeze solid, rendering the attitude control thrusters useless. Without power to the transmitter, the signal dies, and the spacecraft becomes permanently unreachable. Without electricity to the computers, the spacecraft tumbles and loses its carefully maintained orientation toward Earth, a condition from which it could never recover. The mission team has been playing a decades-long game of triage, shutting down instruments one by one to conserve power for the essentials. The ultraviolet spectrometer, which studied planetary atmospheres, was turned off in 1998. The planetary radio astronomy instrument, which measured radio emissions from Jupiter and Saturn, went dark in 2007. The plasma science instrument, which measured the speed, density, and temperature of the solar wind, was deactivated in 2007 after it had fulfilled its primary mission. Each shutdown bought a few more years of operation, but each one also narrowed Voyager's scientific capabilities. By 2030, NASA estimates they'll have to shut down the last remaining science instruments, the cosmic ray detector and the magnetometer, to keep the transmitter and attitude control systems running. By 2036, maybe 2037, if they're lucky, Voyager 1 will go completely silent. Not from a catastrophic failure, not from a collision with space debris, but from simple power starvation. The lights will dim, the transmitter will weaken, and eventually the signal will fade below the detection threshold of even the most sensitive radio telescopes on Earth. The November 2023 glitch nearly ended everything early, years before the power should have run out. The problem started in Voyager's Flight Data System, or FDS, one of 3 onboard computers responsible for packaging science data before transmission to Earth. The FDS collects readings from all the instruments, formats them into a coherent data stream, and passes them to the telemetry modulation unit, which then beams the signal back to Earth via the high-gain antenna. Suddenly, on November 14, 2023, instead of binary-coded messages containing temperature readings, particle counts, and magnetic field measurements, the spacecraft started sending a repeating pattern of 1s and 0s that contained no useful information whatsoever. It was as if Voyager had suffered a stroke, losing the ability to form coherent thoughts, but still trying desperately to communicate. The engineering team, based at NASA's Jet Propulsion Laboratory in California, faced an impossible diagnostic challenge. The spacecraft is so far away that radio signals traveling at the speed of light, 186,000 miles per second, take 22.5 hours to reach it. Send a command, wait 22.5 hours. Receive the response, wait another 22.5 hours. Every troubleshooting attempt required 45 hours of round-trip communication time, and that's assuming the commands worked correctly on the first try. And they were working with hardware built in the 1970s, using programming languages and architectures that barely exist anymore. The FDS was programmed in assembly language, a low-level code that speaks directly to the processor, written by engineers who are now retired or have passed away. Many of the original engineers who designed Voyager's systems are no longer alive to consult. The documentation, while extensive, is incomplete in places, with handwritten notes and corrections that reference design decisions lost to time. Some of the tools used to build Voyager, the custom test equipment, the programming interfaces, don't exist anymore. Modern computers can barely emulate the ancient hardware. The team spent months testing hypotheses, sending diagnostic commands, analyzing the garbled responses. They tried isolating different subsystems. They tested memory locations. They checked for radiation damage. They even considered the possibility that cosmic rays, high-energy particles from distant supernova explosions, had flipped bits in the computer's memory, causing random errors. Finally, in March 2024, after exhaustive analysis, they identified the culprit. A single memory chip in the flight data system had failed, likely corrupted by a cosmic ray or simply worn out after 46 years of continuous operation. The chip contained critical code that packaged the science data, and without it, Voyager couldn't communicate properly. The spacecraft was still alive, it was still receiving commands, but it had lost the ability to tell us what it was seeing. The solution required a level of precision that borders on miraculous. The team couldn't simply replace the chip, obviously. They couldn't reboot the system because there was no guarantee it would restart correctly. They couldn't even access the full memory map directly. Instead, they had to relocate the corrupted code to a different part of Voyager's memory, a section that hadn't been used in decades, then verify that the relocated code still functioned correctly. This was complicated by the fact that Voyager's memory is divided into multiple partitions, and moving code between partitions required careful recalculation of memory addresses and jump instructions. They spent weeks writing the patch, testing it on ground-based simulators, running worst-case scenarios. One mistake, one incorrect memory address, one timing error, and they could permanently brick the spacecraft. On April 18, 2024, they transmitted the new instructions, and then they waited. 2 days later, 45 hours of signal travel time, Voyager 1 responded with clear, coherent data for the first time in 5 months. Temperature readings, particle counts, magnetic field measurements, all formatted correctly, all transmitted successfully. The engineering team had successfully performed remote brain surgery on a 46-year-old computer located 15 billion miles away, using technology older than most of the people in the room. But the fix was temporary, a band-aid on a deeper problem. The underlying issue remains. Voyager's hardware is failing, one component at a time, and eventually, there won't be enough working memory to reroute critical systems. The cosmic ray environment in interstellar space is harsh, with particles constantly bombarding the spacecraft's electronics. Modern spacecraft have radiation-hardened chips designed to withstand this abuse, but Voyager was built before anyone understood the long-term effects of deep space radiation. Every day that passes increases the probability of another failure, another memory chip corrupted, another system degraded. The November glitch was a warning, a preview of the kind of failures that will become more frequent as the spacecraft continues to age. Next time, they might not be able to fix it. Next time, the corrupted code might be in a section they can't relocate. Next time, Voyager might not respond at all. Voyager 1's journey through the outer solar system rewrote textbooks and fundamentally altered our understanding of planetary science. At Jupiter in March 1979, it discovered active volcanoes on the moon Io, the first time volcanic activity was confirmed on any world other than Earth. The discovery was accidental. Engineer Linda Morabito was examining navigation images when she noticed a strange umbrella-shaped plume extending hundreds of kilometers above Io's surface. Further analysis revealed 9 active volcanoes, with material being ejected at speeds up to 1 kilometer per second, fast enough to escape Io's weak gravity. The source of the volcanic activity turned out to be tidal heating, the gravitational tug-of-war between Jupiter, Io, and Jupiter's other large moons, which flexes Io's interior and generates immense heat. This discovery revolutionized our understanding of how moons stay geologically active. It revealed that Jupiter's Great Red Spot was far more complex than anyone imagined. A storm system with internal structures, wind speeds exceeding 400 miles per hour, and dynamics that defied prediction. The storm had been observed since 1830, but Voyager showed it was layered, with multiple altitude levels rotating at different speeds. Voyager photographed Europa's icy surface, noticing cracks and ridges that suggested a subsurface ocean, a discovery that would later make Europa a top target for the search for extraterrestrial life. The surface was remarkably smooth, lacking the impact craters that mark every other solid body in the solar system, suggesting that something was constantly resurfacing it from below. Scientists now believe Europa harbors a liquid water ocean beneath its icy crust, kept warm by the same tidal heating that powers Io's volcanoes, and that ocean could potentially harbor life. Voyager also studied Ganymede, the largest moon in the solar system, larger even than the planet Mercury, and discovered it had its own magnetic field, the first moon ever found with this property. At Saturn in November 1980, Voyager captured the most detailed images of the planet's rings ever taken, revealing thousands of individual ringlets, braided structures, and gravitational resonances caused by shepherd moons. The rings weren't solid or uniform. They were made of countless ice particles, ranging from dust grains to house-sized boulders, all orbiting Saturn in intricate patterns governed by gravity, collisions, and electromagnetic forces. Voyager studied Titan, Saturn's largest moon, detecting a thick, nitrogen-rich atmosphere that obscured the surface completely. The atmosphere was denser than Earth's, with surface pressure 1.5 times that of sea level on our planet, and it extended hundreds of kilometers into space. That discovery launched decades of speculation about what might exist beneath Titan's orange haze, questions that wouldn't be answered until the Cassini mission and its Huygens probe landed there in 2005 and discovered lakes of liquid methane, riverbeds carved by hydrocarbon rain, and a complex organic chemistry that resembles a frozen version of early Earth. After Saturn, Voyager 1's trajectory flung it upward, out of the plane of the solar system, toward the constellation Ophiuchus at a speed of 38,000 miles per hour. It would never encounter another planet, it would never photograph another moon, it would never see another ring system. Its planetary mission was over, but its journey into the unknown was just beginning. For the next 3 decades, Voyager 1 drifted through the outer reaches of the solar system, passing through a region dominated by the solar wind, a stream of charged particles, mostly protons and electrons, flowing outward from the sun at over 1 million miles per hour. This wind isn't gentle, it's a supersonic plasma stream that carries the sun's magnetic field with it, creating an enormous bubble called the heliosphere, a protective shield that deflects most of the galactic cosmic radiation that would otherwise bombard the inner solar system. Without the heliosphere, life on Earth would be exposed to far more dangerous radiation, enough to make the surface potentially uninhabitable. Scientists knew the heliosphere had a boundary, a point where the solar wind weakens and interstellar space begins, but nobody knew exactly where that boundary was, how thick it might be, or what it would look like. Some models predicted it would be smooth and gradual, others suggested it would be turbulent and chaotic. Voyager was heading straight toward it, and it would be the first spacecraft ever to reach this frontier. On August 25, 2012, at a distance of 121 astronomical units from the Sun, roughly 11.3 billion miles, Voyager 1 crossed the heliopause and entered interstellar space. It became the first human-made object to leave the solar system's protective bubble and enter the space between the stars. The crossing wasn't dramatic in any cinematic sense. There was no sudden shift, no obvious marker, no bright line in space. The solar wind didn't stop abruptly. Instead, Voyager's instruments detected a gradual change that took place over several weeks. The density of solar particles dropped steadily, the intensity of galactic cosmic rays increased, the direction of the magnetic field shifted, though not as dramatically as scientists expected. Over several months, Voyager transitioned from a region dominated by the sun's influence to a region dominated by the interstellar medium, the sparse gas and dust that fills the space between stars. The transition was confirmed by analyzing multiple data sources: the plasma wave instrument, the cosmic ray detector, the magnetometer, all showing consistent changes that pointed to the same conclusion. Voyager had crossed the threshold. What Voyager found in interstellar space surprised scientists and challenged many predictions. The region wasn't empty or quiet, it was filled with activity. Plasma waves, oscillations in the electrically charged particles of interstellar gas, rippled through the medium at regular intervals, sometimes lasting for months. These waves were generated by distant events, solar storms that reached the heliopause and sent ripples into interstellar space, density fluctuations in the local interstellar cloud, magnetic reconnection events, cosmic rays, high-energy particles from distant supernova explosions bombarded the spacecraft constantly at intensities far higher than anything encountered inside the heliosphere. These particles had energies measured in billions of electron volts, enough to damage electronics and pose a serious radiation hazard to any future crewed missions. The magnetic field twisted and shifted in ways that didn't match any models, suggesting that the interstellar medium has structure and dynamics far more complex than the simple uniform field scientists initially predicted. The interstellar medium turned out to be denser than expected, with about 0.1 atoms per cubic centimeter, mostly hydrogen with traces of helium and heavier elements. That might sound empty, but it's actually dense enough to exert measurable pressure on the heliosphere, compressing it, shaping it, sculpting its boundaries. Voyager's plasma wave instrument, designed originally to measure plasma oscillations around Jupiter and Saturn, became one of its most valuable tools in interstellar space. The instrument detects oscillations in plasma density, which occur when something disturbs the local environment, a solar storm, a cosmic ray burst, a change in magnetic field strength. Scientists could convert the plasma wave data into audio frequencies, creating eerie recordings that sounded like whistles, hums, and rumbles. These weren't sounds in the traditional sense. Sound can't travel through the vacuum of space, but they revealed the dynamic nature of interstellar space. The medium wasn't static, it responded to distant events, propagating disturbances across light years, creating ripples and waves that Voyager could detect. Some of these plasma wave events lasted for years, starting and stopping with no obvious pattern, suggesting that the local interstellar environment is influenced by processes we don't yet understand. The medium has a temperature, measured in the way particles move, of about 15,000 Kelvin, far hotter than anything inside the heliosphere, but still cold by astrophysical standards. It has a pressure, measured by particle density and magnetic field strength, that pushes back against the solar wind, limiting how far the heliosphere can extend. But every discovery comes at a cost, and every transmission drains Voyager's dwindling power reserves. Every instrument still running brings the spacecraft closer to the day when it will have to be shut down. The mission team has already made painful choices, decisions that required balancing scientific value against operational necessity. In 2019, they turned off one of Voyager's heaters to conserve power, a risky decision because the spacecraft's instruments were never designed to operate at such low temperatures. The engineering specifications called for minimum operating temperatures well above what Voyager would experience without the heater. But the gamble worked. The instruments, built with safety margins and conservative estimates, continued functioning even in the extreme cold. The decision bought a few more years of operation, but it also demonstrated how close to the edge the mission team is operating. Every decision now involves risk. Every power-saving measure pushes the hardware into untested territory. They estimate that by 2025, they'll need to shut down another instrument to keep the transmitter and attitude control systems running. The cosmic ray detector or the magnetometer will have to go, both of which are still producing valuable data about interstellar space. By 2030, the last science instruments will go dark, leaving only the transmitter and the attitude control system operational. By 2036, maybe 2037 if they manage the power budget perfectly, the transmitter itself will fail, not from a mechanical breakdown, but because there won't be enough power to generate a signal strong enough to reach Earth across 16 billion miles of empty space. When Voyager 1 finally falls silent, and it will, the silence will be permanent. There's no possibility of restarting the spacecraft, no chance of a dramatic rescue mission, no hope of restoring power. It won't stop moving though. It will continue its journey through the galaxy forever, coasting at 38,000 miles per hour, faster than any spacecraft ever built. The spacecraft is on an escape trajectory, meaning it will never fall back toward the sun, never be captured by another star's gravity, never collide with a planet or asteroid. It will drift through the Milky Way for billions of years, outlasting Earth itself. In 40,000 years, it will pass within 1.6 light-years of the star AC plus 79 3888, a red dwarf in the constellation Camelopardalis, a dim star invisible to the naked eye from Earth. In 296,000 years, it will pass within 4 light-years of Sirius, the brightest star in Earth's night sky, a blue-white star 25 times brighter than the Sun. Eventually, Voyager will complete one full orbit around the center of the Milky Way galaxy, a journey that will take 225 million years. By that time, Earth will be unrecognizable. The continents will have shifted, the climate will have changed, species will have evolved and gone extinct. Human civilization, if it still exists, will have either spread across the stars or vanished completely. The Sun will be brighter, hotter, slowly expanding as it ages, and Voyager 1, carrying its golden record, a time capsule of sounds and images from 1977, will still be out there, drifting silently through the cosmos, a monument to a species that looked up at the stars and wondered. The Golden Record is one of the most poignant aspects of the Voyager mission and arguably one of the most optimistic gestures humanity has ever made. Designed by a team led by Carl Sagan, the astronomer and science communicator who believed deeply in the possibility of extraterrestrial intelligence, the record contains 116 images encoded in analog form, greetings in 55 languages, natural sounds like thunder, wind, ocean waves, bird songs and animal calls, and 90 minutes of music from cultures around the world. The music ranges from Bach and Beethoven to Chuck Berry and Blind Willie Johnson, from traditional Japanese shakuhachi to Peruvian pan flutes, from Javanese gamelan to Navajo night chants. The selection was meant to represent the breadth of human creativity, a snapshot of what we sounded like in the late 1970s. The record also includes printed diagrams showing Earth's location in the galaxy relative to 14 pulsars, neutron stars that emit radio pulses at precise intervals that serve as cosmic lighthouse beacons, and instructions for how to play the record, assuming any alien civilization that finds it can decode the symbols. The likelihood of the record ever being found is vanishingly small, almost impossibly low. Space is vast beyond human comprehension. The distance between stars is measured in light years, distances so large that even traveling at Voyager's speed, it would take 80,000 years to reach the nearest star. The Milky Way contains between 200 and 400 billion stars, and Voyager is a single object 12 feet tall and 4 feet wide, drifting through an ocean of emptiness. Even if another civilization exists in our galaxy, and even if they possess the technology to detect and intercept small objects moving through interstellar space, the odds of such an encounter are astronomically low. The record could drift for trillions of years and never come within a light year of another civilization. But the record wasn't really meant for aliens. Not primarily, it was meant for us, a message to ourselves about who we were in 1977 and what we hoped to communicate to the universe. It's a statement that humanity was here, that we looked up at the stars and wondered, that we asked questions about our place in the cosmos, and that we sent a piece of ourselves into the infinite darkness as an act of hope and defiance against the vast indifference of space. Voyager's legacy extends far beyond its scientific discoveries. As impressive as those are, it proved that human-made machines could survive and operate in environments we never fully understood, that spacecraft could adapt to conditions far beyond their design specifications. It demonstrated that with clever engineering, dedicated teams, and a willingness to take calculated risks, spacecraft could far exceed their design lifetimes, turning 4-year missions into 5-decade journeys. It inspired generations of scientists and engineers who grew up seeing Voyager's photographs of Jupiter's storms and Saturn's rings, images that appeared in textbooks, documentaries, and museums around the world. Those images changed how we see our place in the solar system, transforming distant planets from dim points of light into real, tangible worlds with weather, geology, and complexity. It reminded us that exploration is never finished, that every answer leads to new questions, that the edge of knowledge is always moving farther away, always revealing new mysteries. And it showed us that sometimes the most profound discoveries come not from arriving at a destination, but from the journey itself, from pushing farther than anyone thought possible, and documenting what we find along the way. Right now, at this moment, Voyager 1 is transmitting data from a region of space 15.3 billion miles from Earth, a distance so vast that it takes light itself 22.8 hours to cross it. Its signal, traveling at the speed of light, reaches Earth as a whisper, a faint electromagnetic wave barely distinguishable from background noise. NASA's Deep Space Network, a collection of massive radio telescopes in California, Spain, and Australia, tracks Voyager 24 hours a day, rotating coverage as Earth spins so the spacecraft is never out of contact. These antennas are engineering marvels themselves, dishes 70 meters in diameter that can detect signals weaker than a single photon of light. Even with this incredible sensitivity, Voyager's signal is fading. Every day, it grows slightly weaker as the plutonium decays and the power available to the transmitter drops. Within a decade, that signal will disappear entirely, falling below the detection threshold of even the most sensitive instruments, and Voyager will become a ghost, a silent artifact tumbling through interstellar space, unreachable and unknowable. But before it goes dark, it will have given us 60 years of continuous operation, more than any spacecraft in history. It will have shown us worlds we never could have imagined, revealed complexities we never predicted, and answered questions we didn't know to ask. And it will have reminded us that even the farthest journeys must eventually come to an end. The comparison to Voyager 2 is worth noting. While Voyager 1 holds the record for farthest distance from Earth, Voyager 2 holds its own distinctions. It's the only spacecraft to have visited Uranus and Neptune, the ice giants that revealed their own bizarre physics. It crossed into interstellar space in November 2018, 6 years after Voyager 1, entering at a different location and detecting different plasma conditions, proving that the heliopause isn't uniform but varies depending on direction and solar activity. Both spacecraft are slowly dying, both sending back their final observations of a realm no human will visit for decades, perhaps centuries. When they finally fall silent, we'll lose our only direct observations of interstellar space, and it could be decades before another mission reaches the same distance. NASA's New Horizons spacecraft, which flew past Pluto in 2015, is heading into the outer solar system but won't reach interstellar space until the 2040s or 2050s, and even then, it might not have enough power to transmit data from that distance. This isn't just a spacecraft dying, it's the closing chapter of humanity's first venture beyond the solar system, the end of an era that began with optimism about exploration and ends with the quiet recognition that space is vast, unforgiving, and indifferent to our machines. Voyager will drift through the galaxy long after human civilization has transformed or disappeared, a messenger from a species that existed briefly on a small blue planet orbiting an average star. And somewhere, embedded in that silent probe, is the golden record, still carrying music, greetings, and images from a world that will have changed beyond recognition by the time anyone, if anyone, ever finds it. This story isn't about aliens or mysteries or cosmic conspiracies, it's about something far more profound. It's about human beings building a machine, sending it farther than anything has ever gone, watching it slowly die, and knowing that we did something that mattered. And it's happening right now, in real time, as Voyager sends back its final transmissions from the edge of everything we've ever known.